Okay, so last time we had stopped at this discussion of concurrence of altitude. So I believe last lecture we proved this fact about the concurrence of medians of a triangle. But a much less obvious fact, I guess, maybe intuitively, before you think about it a bit, is the concurrence of altitudes. And so the real trick here to make this a very simple proof is the following. To prove this, what I'm going to do is I'm going to choose my point as the origin to be very convenient for my diagram, basically. Okay, and so the idea is, say that I have a triangle. Okay, so I'm going to draw the triangle first. So here's my triangle. Okay, so let's say there's my triangle, and let us pick. Say, a couple of these altitudes to draw in. So the altitudes are the perpendiculars from the vertices to the opposite side. So I'm going to pick one here. So here's one. Okay, and then let's pick another one that is the perpendicular to this. So we always get an intersection in this way. So I'm going to call this intersection my origin. All right, so there's my origin 0. I can set the origin there. There's no issues with that. I can just assume that I've drawn this diagram in such a way that that this point is the origin. And so once I've done that, I'm now going to label these points. So let's say that my vertices for my triangle I label as the vectors u, v, and w. Okay, and so I've drawn in two of these altitudes, and they intersect at this point that I'm calling the origin. Now, the thing that I'm trying to prove is that if I draw in the line from the origin to w, that line, so I'm going to draw that as a dashed line. So what I am trying to prove is that if I draw in this dashed line like this, if I extend that all the way to this opposite side, that dashed line is actually the perpendicular to this side from u to v. And if that's the case, then I have the concurrence of altitudes, right? I have this perpendicular, which is unique, right? In this way, is actually it actually passes through that same point that the other two altitudes pass through. Okay, so this is what I'm trying to show. So I want to show that in this configuration, W is perpendicular to, so when I say W, of course, I'm including in that interpretation the line segment from 0 to W, right? That's what I mean by that. So I want to show that W is perpendicular to this opposite side, that is the line segment from U to V. But how do I write that in vector form? Well, V minus W, right? Or sorry, V minus U. Right? So this is what I'm trying to prove. Okay. Now, when I say in this configuration, what is this configuration? So the configuration, my setup is everything I drew that's not a dashed line. Okay, so it's everything else. What does this setup tell me? So since, for instance, the fact that I drew in this perpendicular here from U to this opposite side, so since U is perpendicular. I'm not going to write out perpendicular. I'm just going to say perp. So since u is perpendicular to the opposite side, w minus v, let's see, then what do we know about that, right? Well, the nicest way to characterize perpendicularity is using the inner product. So this means that u dotted with w minus v is 0. Right. Now I can use the algebraic properties of the inner product to say this means that u dotted with w minus u dotted with v is 0. Okay, so that's what I get out of that. Okay. Now, furthermore, so that's using the fact that this line I drew is perpendicular to the opposite side. So I'm going to do the same thing for the other altitude that's solid here. So since v is perpendicular to the opposite side u minus w, then v dotted with u minus w is equal to 0, which similarly, using algebraic properties of the inner product, means that v dotted with u minus v dotted with w is equal to 0. Okay. Okay. So then what I want to do is add these. So I add those things. So adding the boxed terms, so adding the boxed expressions, what do I get? I get u dotted with w minus u dotted with v plus v dotted with u minus v dotted with w. Says what? What is this? So this is equal to 0, since both of these things are equal to 0. Okay, but what do you notice? Well, u dotted with v and v dotted with u are actually the same thing, right? This is one of those fundamental properties of the inner product. And so this can be rewritten as u dot v, but this is minus u dot v, and so these things cancel. All right, so these terms cancel, and what I get here is u dotted with w minus v dotted with w is equal to 0. But then using this distributive property of the dot product, again, what does this say? This says that w dotted with v minus u, if you like, since I wrote v minus u here. But that's exactly what I was trying to show. All right. So this says, using that fact that the dot product tells me when two vectors, or when two line segments determined by vectors are perpendicular, this finishes the proof. This says that w is perpendicular to that other side. So this dashed line is actually perpendicular. And so those altitudes all meet at that point 0. Okay. All right. All right, so that's the proof of that fact. That gives us another nice application of dot products. So these are facts that are a little trickier to prove if you use something else. So this gives us a really nice way to prove these facts. All right. Okay. So more about the inner product. Let's talk about the inner product and cosine, or the relationship between the inner product and the angle between vectors. So you've seen this relationship before, but it's important enough to note that the inner product u dot v depends not only not only on the length of the vectors in question, but also the angle between them. Specifically, you already know that it depends on the cosine of the angle between them. Okay, but as mentioned previously, we don't want to get into the hassle of measuring angles, because technically then we're moving into like the analytic realm, and things become more complicated when we have to talk about things like that. So what I want to do is completely avoid that, and define cosine in a way that is going to be convenient for us to not have to do anything like that. So rather than measuring angles, I want to define cosine as the ratio of sides of some right triangle, right? So I'm essentially here using SOHCAHTOA, right? So if I have a right triangle, oh, I went too far. If I have a right triangle here, and we'll say I put the origin here at this left vertex, and I have other vertices determined by vectors u and v, so that this side length, of course, is the length of u. The hypotenuse, in this case, is going to be the length of v here. Okay, and then this angle here in the corner at the origin is my angle theta. Okay, then cosine of theta is defined to be the adjacent side over the hypotenuse, right? So this is the definition of cosine for us. All right. Okay. So this is going to make things convenient for us when we want to not get into actually measuring angles in some other way, right? This keeps us using convenient language here. And so we have the following inner product formula. So this is the inner product cosine formula, if you like. So if theta is the angle between vectors u and v, then u dot v is equal to the length of u times the length of v times cosine of theta, the angle between them. Okay. All right. So again, you've seen this formula before. Okay, but where does the cosine come from? So it turns out this is actually just some very simple algebra trickery. So what do? So I look at this triangle that I've drawn, and what do I know about this triangle? Well, in this triangle, I've drawn it as a right triangle here. Here's the right angle, right? So this vector v is the hypotenuse here. And so the statement that this is a right triangle is just the statement that this vector, which is the vector v minus u, is perpendicular to u, right? So u is perpendicular to v minus u, right, since that's a right triangle, i.e. U dotted with v minus u is equal to 0. But what does this say? Well, this says that u dotted with v minus u dotted with u is equal to 0. So what does this say? So I can move this to the other side. So this says that u dotted with v is equal to u dotted with u. Okay. But then that's equal to what? A vector dotted with itself we could think of as being the length of vector u squared. And this is this is the relationship between the inner product and length of a vector. So the length of u squared is equal to u dotted with v. But then there's another way of writing this. I can write this as the length of u times the length of u. Okay. How does that help me? Well, so long as v is not the 0 vector, right? And we can definitely say that we don't care about v being the 0 vector, because dotting something with the 0 vector is going to be 0, so it's not an interesting case. We can totally toss that out. If v is not the 0 vector, then I can also say that this is the same thing as multiplying this expression by length of v divided by the length of v. Right. That's a trick I can do. And when I do this, what do I get? Rearranging, I get length of u times length of v times length of u over the length of v. But we said that the length of u over the length of v is cosine. So what is this expression? So this expression then is length of u times length of v times cosine of theta. And that's it. Okay. All right. So that's a pretty funny way to show this formula, but this is how it works. This is a nice formula that relates. So not only then is the inner product related to notions of length and distance, but it's also related to angles, or at least the cosine of angles, which means it's related to the measuring of angles. Okay, so that's pretty nice. This is a pretty big tie-in. This says that our inner product is entangled with literally everything we care about, right? All those quantities that we care about traditionally in geometry, right? Like distances and angle measurements, those are related to the inner product in some way. So this is important. Note the special case, right? Because you know what cosine of pi over 2 is. Note that when these things are perpendicular, you have length of u times length of v times cosine pi over 2, which is 0. And so you get that their dot product is 0. So this is, in a backwards way, it also shows why you get this fact that these are u and v are perpendicular if and only if their dot product is 0. Okay. So continuing on here, something I had mentioned before when we actually talked about the dot product for the first time, one of those properties, one of those things we algebraically computed was the following, or it is equivalent to the following, and the proof of it is literally going to be the inner product formula we just did together with that algebraic fact. So this is the law of cosines. What is the law of cosines? Okay, so if you remember correctly, right, in high school you had law of sines, which you might not remember, and I'm not even going to state now, which was, it was it was about the ratios of sines to the ratios of sines all being equal. But the more important thing to use was the law of cosines, because it applied to any triangle. It was basically a thing kind of sort of like the Pythagorean Theorem, except you could apply it to any triangle. It didn't have to be a right triangle, right? So what does the law of cosines in our sense say? So in any triangle, so let's say that our sides, so with sides u, v, and u minus v, and angle theta opposite the side u minus v, the length of u minus v squared is equal to the length of u squared plus the length of v squared minus 2 times the length of u times the length of v times cosine of that angle theta opposite the side u minus v. Okay. So what's the proof of this? So I'm going to show you the picture in a second to show you where, how the law of cosines that you remember from high school comes up here. But this is actually, you don't need the picture at all, because this is purely algebraic. So I wanted to compute the length of a vector squared. What do I do, right? What's the easiest way to do that? The easiest way to do that is to just dot the vector with itself. So this is u minus v dotted with u minus v itself, right? Okay. But when I do this dot product out, what do I get? I get u dotted with itself. And then I'm going to get, say, minus v dotted with u. And I'm going to get minus u dotted with v. But u dotted with v, v dotted with u are the same things, and so I can just combine those. So I get the mixed term minus 2 times u dotted with v plus v dotted with itself. Okay. So reorganizing those, and this is the statement that we got when we first talked about this, and I told you at the time that this was equivalent to the law of cosines. So that statement is u dotted with itself, that's the length of u squared. V dotted with itself is the length of v squared. Minus 2 times u dotted with v. We're almost done though. I want to use the fact that u dotted with v is the length of u times the length of v times cosine of theta. Right? Let's make sure that that theta, coming from that, actually lines up to be the side opposite u minus v. It does, and I'll show you in the picture here in a second. So this becomes length of u squared plus length of v squared minus 2 times length of u times length of v times cosine of theta. That's exactly what I wanted to prove. Okay, so this proof is 100% algebraic, relies on algebraic properties of the dot product, together with that formula that we just proved. Okay, that's where we get this. Now, how is this the law of cosines from high school? So to show you what this setup looks like, it's a little bright. Okay, so to show you what the setup looks like, here's the triangle in question. So the triangle in question, I have vertices 0, u, and v. So then side lengths, length u, length v. This side, right, the line segment from u to v or v to u can be thought of as u minus v or v minus u. The length of that's the same, so the length of u minus v is what I'm looking at here. So the angle opposite is theta. So then it being the angle opposite this side u minus v makes it the angle between u and v. So of course this substitution that I did using this fact here was correct. Okay. All right. And so that's how it is actually, that's how it turns out to be the law of cosines you knew from high school. So note, this is actually a special case, or I should say, the Pythagorean theorem is a special case of this law of cosines. Right? Okay. So note, if the triangle in question is a right triangle with side u minus v being the hypotenuse, then the law of cosines becomes the Pythagorean theorem. So to see that, I look at law of cosines. If u minus v is the hypotenuse, right, then I would have length of hypotenuse squared is length of u squared plus length of v squared minus 2 times length of u times length of v times cosine of, well, if u minus v is the hypotenuse, theta is the angle across from the hypotenuse. So this is cosine of pi over 2. Okay, and what is that? What is cosine of pi over 2 here? Well, cosine of pi over 2 is 0, right? You know, what is a way that I could say that without having to invoke cosine pi over 2 is 0? Because if you try to look at this and say, cosine pi over 2 being 0, but I defined cosine as the ratio of, you know, the length of u to length of v in that one triangle setup, and so like how could that be 0 unless that top length is 0? That doesn't hardly make sense. So this is a little confusing. Okay, this is a little confusing here. Now, you know, of course, that cosine pi over 2 is 0, but how can I make sense of that in the way that I've done? So let's look back at this proof. We also know that we have this fact algebraically, right? So algebraically, I could have written here instead that the length of the hypotenuse squared is the length of u squared plus the length of v squared minus 2 times u dotted with v. Okay, but because this is a right triangle, u minus v is the hypotenuse, that means u and v are perpendicular, right? The angle between them is pi over 2. U and v are perpendicular, this is 0. So I don't need to reference cosine at all. I can actually just say this is 0. In fact, I can use the previous fact about the dot products being 0 when u and v are perpendicular to define cosine of pi over 2 to be 0. Okay. So that's one way of looking at it to avoid this. And so what is this? This is saying the length of the hypotenuse squared is equal to the sum of the squares of the other two legs. So this is the Pythagorean theorem. So that's the Pythagorean theorem. Now, if you think about it for a second, so while that might seem really cool and nice, but if you think about it for a second, this actually isn't that amazing because I'm cheating a little bit and doing something kind of circular. Because I had already shown in chapter 3 that the Pythagorean theorem is baked into our notion of distance, right? So using our coordinate notion of distance, right, that distance formula, that actually uses the Pythagorean theorem itself. So the Pythagorean theorem is basically true by definition, using that definition of distance. Okay. And then so where is the Pythagorean theorem already baked in kind of? It's baked into the dot product, since the dot product is what gives the distance. Okay, since the dot product gives the distance and then the distance has baked in it the Pythagorean theorem, it's not surprising that the Pythagorean theorem would be related to this expression. Okay, so the Pythagorean theorem is actually built into the definition of distance and into the inner product because of that. Okay, and so it really is the assignment of the inner product that is determining the geometry. That is a point that I harp on over and over and over again. But it turns out that that is an extremely important observation. It's a very subtle thing because this was something that mathematicians didn't figure out until much, much later. That this was a thing, and mathematicians of extremely high caliber, this completely eluded them. They were not able to put the pieces together to see how important these basic facts were to what would come later. Okay, so anyway, that's that. All right. And so now I debated on whether or not I would give you the assignment to prove the triangle inequality in a more painful way, but I decided not to. So I decided not to, since we'll prove it now in a less painful way. But I might in the future have you prove it, or I might do something with it later where you do it in a slightly more painful way. This uses something called the Koshi-Schwarz inequality. So what is the triangle inequality? The triangle inequality is the statement that the length of the sum of two vectors, u and v, is less than or equal to the length of the two vectors summed individually. Okay. That's the triangle inequality. Okay. All right. So to prove this, we first consider another inequality that might seem too simple to have a special name at first, but I'll explain why it has a special name here in a second. So there's an inequality called the Cauchy-Schwarz inequality. So the Cauchy-Schwarz inequality says what? Maybe I should write it out. The Cauchy-Schwarz inequality. What does this say? It says that the absolute value, so this is a scalar, right? So when I slap on these absolute value signs around a scalar, it is the absolute value. So the absolute value of u dotted with v is less than or equal to the lengths of u and v multiplied together. Okay. So let's prove this. Okay, so a quick proof. The absolute value of u dotted with v, okay, is less than or equal to the absolute value, or sorry, the length of u dotted with the length of v times the absolute value of the cosine of theta. Where does that come from? That comes from, of course, our formula that the dot product between two vectors can be viewed as the product of their lengths times cosine of the angle between them. Okay. So if I slap an absolute value sign on that, absolute value of u dotted with v is less than or equal to the length of u times length of v times the absolute value of cosine of theta. But this is less than or equal to the product of the lengths of u and v, since the absolute value of cosine theta, we know, is always less than or equal to 1. So that's it. Okay, so that was a pretty quick thing to prove. So here's Cauchy-Schwarz inequality. Now, to see how I get the triangle inequality from this, so proof of triangle inequality is the following. So we show that the length of u plus v squared is less than or equal to the length of u plus the length of v squared. Right? This is sufficient because squaring something is going to be it's going to be enough for us to say the triangle inequality. From this fact. So this is sufficient. So this is sufficient for us. And so the length of u plus v squared is best computed as dotting that vector with itself. Okay. You know, in these sorts of proofs in general, when you have proofs of inequalities or any kind of facts involving distance formulas, you don't want to be working underneath a radical typically, and so this squaring of it to make the algebra work out nicer is something that is common to do. So let's expand this using products of the inner product. So this is u dotted with itself, which I'm just going to go ahead and write as the length of u squared, plus the mixed term, which is v dotted with u and u dotted with v. So u dotted with v and v dotted with u. Of course, those are the same thing. So the mixed term is 2 times u dotted with v. Okay, plus v dotted with itself, which I'm just going to rewrite as the length of v squared. Okay. All right. Okay, how does this help me? Well, I can always slap an absolute value sign on here if I'm willing to introduce an inequality. But slapping an absolute value sign on here means I could use Cauchy-Schwarz to split this as a product of lengths. And so by Cauchy-Schwarz, this is less than or equal to the length of u squared plus 2 times the length of u times the length of v plus the length of v squared. But now I get exactly what I want. Of course, this is just the expanded form of the length of u plus the length of v squared. And so from this, I get the triangle inequality, which I'm going to rewrite here. That is, the length of u plus v is less than or equal to the length of u plus the length of v. Okay. Now, a couple of words here. So one, why is something so simple as the Cauchy-Schwarz inequality, why does it have a name, right? Why are there names, or two names even, associated to this inequality? So the reason why is that the Cauchy-Schwarz inequality holds in much more general settings than just this real vector space or Euclidean space that we're going to be talking about. And so this is an important inequality, not just for us in this setting. It's a much more general thing. Cauchy-Schwarz inequality holds much more generally when the thing you're talking about is not just the Euclidean length of vectors. Okay, and so if you're interested in that, you could have a look. You can look up Cauchy-Schwarz inequality. In the same vein, because the Cauchy-Schwarz inequality is usually used to prove the triangle inequality. The triangle inequality, the same exact thing is true for it. It holds in more general settings. In fact, depending on the context in which you encounter it, a lot of times the triangle inequality is assumed as a sort of axiom. So this is important for us. It's important in any time you're doing something involving wanting a distance function. This is important. And the reason why, this is actually taken as one of the axioms of what are called metric spaces. So if you've never encountered a metric, well, you've definitely encountered a metric space before, because pretty much all the spaces you've seen are examples of metric spaces. But a metric space is just a set that has been equipped with a distance function that behaves like the distance function that you're used to. Okay, so it behaves like Euclidean distance, all right? And so this is Euclidean distance, so it is the model on which all metric spaces and all metrics are based. All right, and so this fundamental fact about Euclidean distance is something that gets baked into more general topics where you're investigating spaces where you're not exactly dealing with Euclidean the notion of Euclidean distance. You're dealing with some notion that is similar to Euclidean distance, but not quite the same. So both of these things, the triangle inequality and the Cauchy-Schwarz inequality, are things that are very important in contexts way more general than ours, and so that's why they have special names. Okay. All right. So then I just wanted to say a couple things, since I had mentioned this, and I even broke out my copy of the elements to show you all the stuff that we're missing, or that we're getting to skip. So here's something I wanted to say. So higher dimensional Euclidean spaces. Okay. So I can talk about Rn just like we talked about R2. This is the set of n tuples, right? So set of real n tuples. So they're ordered. So it matters, right, in what slot we're talking about. So our n tuples are like our ordered pairs. It's just that rather than having two entries, there's n of them. Of course, you've seen this in the case of R3 previously, but we can do this for arbitrary n here. These are called n-dimensional vectors. Okay, I don't need to get into, I don't have to spend too much time defining what I actually mean by dimension, but for us, the dimension will be apparent from the thing that we're dealing with, what dimensional space we're talking about. But we could get more into that, but that's not the direction we're going to go, so I'll leave that. So if you have two vectors u and v, the notation for them is the obvious thing. If you have both of those in Rn, of course, their vector sum is going to be the sum component-wise, so u1 plus v1, u2 plus v2, and so on, all the way up to un plus vn. So our vector sum works the same way. Scalar multiplication works exactly the same way. Okay. So we have those basic vector operations that we want. We can define the dot product, of course, in the exactly analogous way. So u1 v1 plus u2 v2, and so on, all the way up to un vn. So we could define that dot product. In the same way, we can define distance. So distance comes from the dot product in the same way. So the length of a vector u squared is the vector dotted with itself, i.e. the distance or the length of a vector is the square root of the vector dotted with itself. Okay, so we define distance in the exact same way. Of course, in R3, what this means in, specifically, so if I look at the example of R3, the length of a vector u is square root of its dot product with itself, so this would be the square root of u1 squared plus u2 squared plus u3 squared. The very familiar distance or length formula or distance formula. Okay. And of course, if you wanted to look at a nice picture of what this setup looks like in space, well, oh, it's taken a while to, there we go. So what this setup looks like in space, you can actually see the two-dimensional distance down below in the plane, and you can see this three-dimensional distance in the usual way that you might see it in Calc 3, right? Okay. Now, all of the theorems that we proved for vectors in the plane are true in Rn, right? So all theorems proved for vectors in R2 in this chapter are also true in Rn. Okay, so they're true in this other setting. In fact, you already know that, of course, I could treat my usual plane, R2, as sitting inside Rn as, say, the x1, x2 coordinate plane, right? But it turns out that any plane you choose in your space actually behaves in the same way, right? In fact, any plane in Rn behaves identically to the canonical, we'll say, copy of R2. Okay, so the usual Euclidean plane you might think of about sitting in space, actually we could use any plane we wanted to. We can use a suitable isometry of Rn that maps any plane to the usual one. Okay. But I just said something. Isometry of Rn. Right? I said isometry of Rn. That's something we haven't studied before. We've studied isometries of R2, but not isometries of Rn. So what is an isometry of Rn? It turns out that this same fact is true. What about isometries of Rn? Well, for R2, any isometry is a product in the sense of function composition, right? So any isometry is a product of reflections. What was the most you needed? So at most, we needed 3. Right? So we needed 3 at most. For Rn, any isometry is also a product of reflections. And at most, we need n plus 1. So this is an important bit. How do I prove this? It is very similar to the one that we did in chapter 3. So very similar to our proof for the R2 case. Very, very similar. Okay. All right. So we have one more thing to discuss before we completely are done with chapter 4. But once we finish that discussion, basically we'll be moving on to our next pillar, right? So this will finish our second pillar, which is the use of coordinates and linear algebra to make some of these geometric arguments so much easier, especially using the fact that now we can talk about Rn, like n-dimensional space. This takes us beyond some of the things that the Greeks could do. One, the Greeks couldn't deal with anything higher than 3-dimensional because they had no way of doing it. Everything required these diagrams, and so they couldn't really do it suitably in their pictures, right? And so the most complicated stuff done in Euclid's Elements were these 3-dimensional Euclidean geometry arguments, which are made so much easier by using coordinates and linear algebra. So anyway, I'll tidy that stuff up, and we'll move on to our next pillar, which is projective geometry. So we'll do that on Wednesday. Okay, so that begins as a discussion of perspective drawing. So it'll actually be a fun thing, and actually no pressure on me trying to draw a bunch of nice pictures live. Okay, so anyway, I will see you all on Wednesday. I'll make an announcement this week about your exam. So your exam will be next week, and I'll tell you everything about it in the announcement. So anyway, I will see you all later.